Hi everyone, let's begin repeated measures ANOVA with the help of Jamovi. First of all, we would understand what is the meaning of repeated measures ANOVA. So, where we are going to apply repeated measures ANOVA that we are going to use when there is a statistically significant difference between the means of three or more groups in which the same subjects show up in each group. So, a repeated measures ANOVA is typically used in two specific situations. Number one, first situation, let me talk about this. Measuring the mean scores of subjects during three or more time points means we are measuring at different time, we are measuring these scores. Like, for example, you might want to measure the marks of students before they start a training program, during the middle of the training program, and the after the training program, after completion of the training program, to see if there is significant difference in mean marks across these three time points. So these are the students' name A, B, C, D, E, F, G, and before training marks in the second column, third column, middle of training marks, and this one last one is the after completion or after training marks. These are the four columns I am having. So what we have to do, another situation is measuring the mean score of subjects under three different conditions. For example, you might have subjects consumed three different soft drinks and rate each one based on how much they enjoyed it. So this one is the same subject show up in each group. So we need to use our repeated measures ANOVA to test for the difference in the means across these three conditions. Right. So name of the subject, this one is the name of the subjects A, B, C, D, E, and soft drink X, soft drink Y, and soft drink Z. These are the three different types of soft drink, and we are measuring, right, how much they are satisfied, or that one is the score. So first of all, what we will do, let me open this Jamovi. I'm just opening this data. Let me open this file and let me browse this. And my file name is ANOVA repeated measures. I would open this file. And after this opening this file, what we will do, simply these are the columns: student name, marks before test, before training, marks middle the training, midpoint of the training, and marks after completion of this training. So what we have to do, first of all, we are exploring their descriptives, right? We will check descriptives. We will shift all the variables, all continuous variable towards the right hand side. And I would check descriptives. And there's the total number of observations are 7 in each category, before, mid, and after. Missing value is 0. Mean value, you can see median, standard deviation, minimum, and maximum. We have to check. But whether this data is normally distributed or not. So first of all, we have to go for this Shapiro-Wilk test, and let me check here. Now we can see Shapiro-Wilk test 0.904, 0.923, 0.944 means this value, it is greater than 0.05. So it means our data is normally distributed. If this value would be below 0.05, that means we are violating this assumption, means our data is not normally distributed. But in our case, this data is normally distributed because Shapiro-Wilk test, that is less than 0.05. Not less than 0.05, it is greater than 0.05. So means our data null hypothesis, that is accepted. That is, we have failed to reject null hypothesis, and it means we can say our data is normally distributed. And let me come for this ANOVA. Now we would start ANOVA. So one-way ANOVA we had already finished. Two-way ANOVA also we had completed in my previous video. I would share all the links in my description box. And repeated measures ANOVA, let me start. A moment we would open this repeated measures ANOVA, this is the RM factor 1, right? So what we have to do, my factor, it is the training. We want to check training impact, right? So my factor is training. And marks, this one is the first category, it is before. I would write, this is the before training, mid of the training, and last one, we are calling it after completion of the training. So these are my before, mid, and after. These are my three categories, right? And here it is repeated measure cells in the before. We will shift. Those are the before training marks. Mid, we have to shift mid of the training marks. And after completion of the training marks in all three categories, I had shifted these marks. So now you can see within the subjective facts, training and residuals, you could be able to see mean squared, F ratio, and P value is 0.001. So this one, it is means we can say P value, it is less than 0.05. That means there is a significant difference among all these three categories, right? Means before training marks, and it means and after training, that is significant difference. Now, what we have to do, first of all, before starting any test, we have to check whether it is not violating any assumption. So, assumptions, first of all, we are going to check for assumption. We would check this box, specificity test. Specificity is one of the important assumption that should not be violated. So here it is, moment we had applied this assumption, test of specificity test, Mushes W, you can see, and p-value 0.566. So it means that means this assumption is not violating, right? But specificity test, what exactly it's doing? So let me just explain you. Specificity is a key assumption that must be satisfied to justify a standard analysis of variance with data from a repeated measures experiment. The specificity assumptions is satisfied when the variance of the difference between scores for any two levels of a repeated measures factor is constant. Right. So it means that is satisfied when there is not much variation. Right. This is the difference between all these things. This one is constant. Right. So that is in my case also this specificity test that is not violating, and my p-value is 0.005. It is less than 0.05. So violation of this specificity is when the variance of the differences between all combinations of the repeated groups are not equal. How we have to check? I had already given this. The violation of this specificity is a serious for repeated measures ANOVA, with violation causing the test to become too liberal, that is an increase in the type 1 error rate. And if the violation of this specificity do occur, corrections have been developed to produce a more valid critical F value, reduce the increase in type 1 error rate. So there are some tests I'm just want to show you here is these are the corrections. So is otherwise by default it is none, because in my case that is fulfilled. Right, there is no violation of a specificity test. If in your case this p-value is less than 0.05, then you can go for corrections, and you have to check this greenhouse geyser test, right? Hohenfeld test, you can check here, and after that you can find out what is happening over here, whether is the corrections that is implementing or not. So what would be happen? That was the mush test of the specificity. That one is the specificity is a formal way of testing the assumptions of specificity, although the test has been heavily criticized. This test, though it was heavily criticized by the statistician, often failing to detect departure from the specificity in a small sample and over detecting them in the large sample. So that was the issue when your sample size is too small, right? So that is detecting departure from this specificity in a small sample, but over detecting when your sample size is too large. So Mushy's test of the specificity test, the null hypothesis that the variance of the differences are equal. Thus, if this Mushy's test of the specificity is statistically significant, p-value should be less than 0.05. So we can reject the null hypothesis. We can reject the null hypothesis and accept the alternative hypothesis that the variance of the differences are not equal. So that means we can say variances of the differences are not equal. So specificity has been violated, right? So this kind of, I'm sure, but in my case, these are my results. And further is how we can analyze this. So Mushy's test of specificity indicating that the assumptions of the specificity had not been violated. In my case, this is not violated, right? That means we are fulfilling this assumption. After that, the corrections that you will encounter to combat the violation of the assumptions of sphericity are the lower bound estimate, greenhouse gaser corrections, and even field correction. These corrections rely on estimating sphericity. And here it is, the degree to which sphericity is present or not is represented by a statistics called this one is epsilon, and epsilon of 1 indicates that the condition of sphericity is exactly met. The further epsilon decreases below 1, it means the greater the violation of the sphericity. Therefore, you can think of epsilon as a statistic that describes the degree to which sphericity has been violated. So, the lowest value of the epsilon can take is called the lower bound estimate. Both the greenhouse geyser and the Winfield procedures attempt to estimate epsilon, right? And in different ways, it is the estimate because we are dealing with samples, not populations. So for this reason, estimates of the sphericity tend to always be different depending on which procedures is used. By estimating epsilon, all these procedures then use their sphericity estimates to collect the degree of the freedom of the F distribution. Lots of things are written here, but how you have to check, you can see greenhouse geyser, this one is 0.831, and Winfield test, that is 1, means exactly we are fulfilling sphericity assumption, that is fulfilled. And in my next video, that would be repeated measures ANOVA part 2. This is part 1, and next one would be part 2, where we have to discuss some more points. Those are related to like post hoc test we will discuss, and we will discuss the second category also to tease all those things. This one is the Bonferroni also we will discuss in the part 2. Right. So I hope this video would be helpful to you. So stay tuned and keep watching.